Namaskar. The topic of discussion in this module is on the properties of seawater. All water existing at or near the surface of the earth belongs to the hydrosphere. It includes atmospheric water vapor, groundwater, lakes, rivers, polar ice caps and the oceans. The waters of the oceans cover more than 70% of the earth's surface. The water that is most often found in nature is the oceanic water or sea water. It is about 98% existing on the globe as seas and oceans. The rest is distributed as ice, water vapor and fresh water on the land. Oceanic water plays a very important role in controlling the global weather and climate. It helps in interactions between the atmosphere and the hydrosphere and maintaining the water balance of the globe. Oceans also provide enormous living and non-living resources for human consumption. Sea water is one of the most fascinating and plentiful substances on the planet Earth. Sea water has a very unique chemistry, physics and biology. The basic properties of sea water and their distribution, the interchange of properties between sea and the atmosphere or land, the transmission of energy within the sea and the geochemical laws which are governing the composition of sea water and marine sediments are the fundamental aspects to be studied under the subject oceanography. To know the role of sea water in the earth's hydrosphere, the following aspects are to be studied or understood first: the physical properties of sea water, the chemical composition of sea water, the biological conditions of sea water, the temperature distribution in oceans and the salinity and density of oceans. Seas and oceans are very huge bodies of saline waters. Their distribution and dynamics are very influential in several ways. The key roles of the oceans are: they absorb and reflect sun's light, they store the heat, they transport the stored heat, they cause major changes in the climatic systems, they are the main source of atmospheric water vapor, they exchange gases with the atmosphere. Understanding the properties of sea water is inevitable in oceanographic studies. Let us see all these aspects in detail. The first part is the physical properties of sea water. The water of the seas and oceans has formed over millions of years ago. Most people do not realize the complex nature of sea water. In fact, sea water cannot be duplicated in any laboratory anywhere in the world. Sea water has its own physical, chemical and biological properties. Due to its huge volume and thickness, it has certain unique characteristics in the distribution of temperature, pressure and density. Most of these properties vary both horizontally and vertically. The physical properties of sea water also act as limiting factors in the marine ecosystems. Water in general is a good solvent. Sea water is an effective solvent. Sea water is also at the receiving end to dissolve all the sediments derived from the land. Rivers carry much of the dissolved organic and inorganic substances towards the sea. These loads increase the salt content of the oceans every year. Sea water has many conservative and non-conservative properties. Sea water has several unique properties like high heat capacity, latent heat of fusion, latent heat of vaporization, latent heat of melting, thermal expansion, density, viscosity and turbidity. Water has the capacity to store heat, conduct heat and release heat. The heat capacity of sea water is the highest of all solids and liquids except the liquid ammonia. The heat transfer in oceanic waters is very high. The latent heat of fusion is also highest in sea water when compared to the other liquids except ammonia. Hence, it acts as a thermostat at freezing point owing to uptake or release of latent heat. The latent heat of evaporation is yet another property which is also the highest in sea water than other substances. It is important for both heat and water transfer to the atmosphere from oceans. Thermal expansion is another important property of sea water. The temperature of maximum density decreases with increasing salinity. For pure water, it is at 4 degrees Celsius. Sea water is also characterized by its surface tension. It is the highest for sea water among all the liquids. Sea water is colorless in small volumes. Due to the presence of organic life and sediment loads near the coast, it may be looking greenish blue or turbid in some places. Blue is the longest wavelength of the colors of the spectrum. Since it is the last one to be absorbed by the ocean, it is the most dominant color reflected in oceanic waters. When descending into the sea, the colors of the spectrum begin to be filtered out. The first color to disappear is the red color. The color of the sea can also indicate several of its properties. In addition to this, sea water also transmits sound. The speed of sound traveling in sea water is also a special feature. It is about 1500 meters per second, and some low frequencies may travel for long distances also in seas and oceans. Hence, it is possible to analyze the depth of the seas and oceans using sound waves. Let us see the second part, the chemical composition of sea water. Sea water is a complex mixture of water, salts and many other organic and inorganic substances. Sea water contains more dissolved ions than other types of water like river water, rain water, lake water and groundwater. Sea water contains 96.5% water, 2.5% salts and smaller amounts of other substances including the dissolved organic and inorganic materials. In addition to that, it contains particulates and few atmospheric gases. The chemical constituents of sea water include many major ions and minor trace elements. In addition, sea water also contains the suspended solids, organic substances and dissolved gases. Sea water chemistry shows 96% water and 4% other elemental constituents. They are: oxygen is 85.84%, hydrogen is 10.82%, chloride is 1.94%, sodium is 1.08%, magnesium is 0.12%, sulfur is 0.09%, calcium is 0.04%, potassium is 0.04%, bromine is 0.0067% and carbon is 0.0028%. The sea water composition is also reflected in the form of salinity. Based on the composition, if we analyze the sea water, the following are the elemental distribution. Oxygen alone occupies about 85.84%, hydrogen occupies about 10.82%, chloride 1.94%, sodium 1.08%, magnesium 0.1292%, sulfur 0.091%, calcium 0.04%, potassium 0.04%, bromine 0.0067% and carbon 0.0028%. Because of this, the sea water is dominated by 6 most abundant ions like chloride, sodium, sulphate, magnesium, calcium and potassium. By weight, these ions make up to about 99% of all sea salts present in the world. When we analyze sea water, the major ion composition of sea water will be invariably showing the following composition in milligram per liter. Chloride is 18,980 milligrams per liter. Sodium will be 10,556 milligram per liter. Sulphate will be 2,649 milligram per liter. Magnesium will be 1,262 milligram per liter. Calcium will be 400 milligram per liter. Potassium will be 380 milligram per liter. Bicarbonate will be 140 milligram per liter. strontium may be 13 milligram per liter, bromide may be 65 milligram per liter, borate may be 26 milligram per liter, fluoride may be 1 milligram per liter, silicate may be 1 milligram per liter, iodide and others may be less than a milligram per liter. The total dissolved solids present in oceanic waters may be about 34,483 milligram per liter. Hence, the total dissolved salts in sea water may come up to 34,383 milligram per liter. It is also expressed in ppm as parts per million. The salt content in sea water is indicated by salinity, which is defined as the amount of salt in grams dissolved in 1 kilogram of sea water, and it is normally expressed in parts per thousand. Salinities in the open ocean have been observed to range from about 34 to 37 parts per thousand. It is denoted as 3.5%. All major ions of sea water are conservative. Though their salt contents vary from one place to the other, their ratios do not change. All these dissolved materials have residence times varying from hours to millions of years. Nitrate has the lowest residence time in sea water, and sodium has the highest residence time in sea water. With reference to the other elements, the concentrations are as follows. Bromine may be 67.3 milligram per liter, inorganic carbon may be 28 milligram per liter, nitrogen may be 15.5 milligram per liter, fluoride may be 13 milligram per liter, strontium may be 8.1 milligram per liter, boron may be 4.45 milligram per liter, silicon may be 2.9 milligram per liter, iodine may be 0.064 milligram per liter, rubidium may be 0.12 milligram per liter, barium may be 0.021 milligram per liter, and uranium is 0.0033 milligram per liter in sea water. Weathering of rocks or minerals and salts introduced into the streams all fed into the oceans as salt contributors. The total quantity of this is on the order of 2.5 billion tons per year. The minerals and salts are also derived from volcanic eruptions known as outgassing from the earth's interior. Of the many minor dissolved chemical constituents, inorganic phosphorus and inorganic nitrogen are among the most notable, since they are important for the growth of organisms that inhabit the oceans and seas. Gas composition changes with time and depth in the oceans. The solubility of gases in the sea water is controlled by the temperature, salinity and pressure. All gases are less soluble as temperature increases. When water is warmed up, most of the gas bubbles leave the liquids. As water temperature increases, the increased mobility of gas molecules makes them escape from the water, thereby reducing the amount of gas involved in sea water. Nitrogen and argon are the inert gases which do not take part in the biological processes of life. Hence, they are not affected by plant and animal life. But the non-conservative gases like oxygen and carbon dioxides are influenced by sea life. Plants reduce the concentration of carbon dioxide in the presence of sunlight, whereas animals do the opposite in either light or darkness. Some other components of sea water are the dissolved organic substances such as carbohydrates and amino acids and organic rich particulates. These materials originate primarily in the upper 100-meter depth of the ocean, where the dissolved inorganic carbon is photosynthetically transformed into organic matter. pH is another important property of sea water. It is reflected in the form of acidity and alkalinity in oceanic waters. The distribution of ocean acidity shows that ocean pH varies from about 7.9 to 8.2. The sea water pH is the lowest in the most productive regions where upwellings occur. It is also thought that the average acidity of the oceans has decreased from 8.25 to 8.14 since the advent of fossil fuels in the world, according to the recent scientific observations. Acid rain falling over the seas may create dangerous situations to many marine biota. Acidity is a limiting factor in marine ecology. Let us see the next aspect, biological conditions of seawater. Biological oceanographers study all forms of life in the oceans from microscopic plants and animals to fish and whales. In addition, biological oceanographers also examine the oceanic processes that involve living organisms. These include processes that occur at molecular scales such as photosynthesis, respiration and cycling of essential nutrients, to large scale processes such as effects of ocean currents on marine productivity. Many biological properties and processes control the abundances and distributions of life in the oceans. In oceans, sun's energy is transformed into organic matter and is also used up by living organisms. Marine organisms exchange matter and energy with each other and with the waters around them. Photosynthesis, chemosynthesis, primary productivity and nutrient cycling are the major processes helpful in marine life survival and maintain the ecology of oceans. The availability of light controls the plant growth and phytoplankton distributions in the oceans. Phosphorus and nitrogen compounds are necessary for phytoplankton growth. These two compounds are more abundant in deep waters than the near surface waters, as they are removed by plants growing near the surface. Seawater is dominated by much amount of dissolved organic matter. Dissolved organic matter remains in the ocean for very long periods of time, maybe many thousands of years. It is roughly equal to the abundance of living matter on earth. There are many sources of organic matter in the seawater. Decomposition of dead plant and animals is one source. Secretion of organic compounds by living plants is also another source. The relative abundance of various forms of organic matter in seawater are: dissolved organic matter 95%, particulate organic matter nearly equal to 5%, phytoplankton 0.1%, zooplankton 0.01%, and fishes may be 0.0001%. Dissolved organic matter enters the food web primarily through tiny bacteria. Particles dispersed in seawater also influence the chemical and biological behavior of seawater. The total amount of particles in the oceans is about 10,000 million tons. The biological particles are relatively large, ranging from 1 micrometer to 1 millimeter. These constitute up to 70% of the particulate matter in the oceans. Particles are also destroyed either mechanically or chemically. These dissolved particles release nutrients, silica and the metals. Hence, the chemistry and biology of seawater is fully influenced by all these properties. The deposition of sediments is also controlled by these masses. Oxygen dissolved in seawater participates in both biological and chemical processes of oceans. It comes from the atmosphere. When nutrients concentrations are high, dissolved oxygen concentrations become low. The oxygen dissolves by diffusion from the surrounding air. Fish and aquatic animals cannot split oxygen from water or other oxygen containing compounds. How much dissolved oxygen an aquatic organism needs depends on the species, the physical state, water temperature, pollutants present and many other factors involved. Numerous scientific studies suggest that 4 to 5 parts per million of dissolved oxygen is the minimum amount that will be supporting a large diverse fish population in oceanic waters. The dissolved oxygen level in good fishing waters generally averages about 9 parts per million. Adequate dissolved oxygen is necessary for good water quality. Oxygen is a necessary element to all forms of life in oceanic environment. The total dissolved gas concentrations in water should not exceed 110%. Concentrations above this level can be harmful to the aquatic life. Fish in waters containing excessive dissolved gases may suffer from gas bubble disease. When an organism dies and decomposes, most of its organic molecules end up in solution as dissolved organic carbon. These molecules are very much smaller than the smallest of organisms like viruses in oceanic waters. Oceans are considered to be the carbon reservoirs. It is evident based on the following statistics. The amount of CO2 dissolved in oceans is about 87.5%. The dissolved organic carbon in oceanic waters is only 7.1%. The biosphere containing all living organisms constitute about 4% of organic carbon. The atmospheric CO2 is 1.4%. These statistics show that oceans are the storehouses of carbon. The future of world's resource needs may have to be met out of these marine resources. Let us see the next aspect, the temperature distribution in oceans. Ocean is the major recipient of sun's radiant energy. It has the capacity to store heat. Many physical processes depend on the temperature of waters. In oceanographic studies, platinum resistance thermometers are used to measure the temperature of waters. The distribution of temperature in the surface of the ocean follows a zonation pattern. It is independent of longitude. The warmest water is near the equator and the coldest water is near the polar regions. Heat fluxes, evaporation, rain, river water inflow, freezing and melting of ice caps all influence the distribution of temperature in the oceans. Changes in temperature and salinity can increase or decrease the density of ocean waters at the surface, which can lead to convection. The temperature of the world's ocean is highly variable over the surface of the ocean. It ranges from 0 degrees centigrade or less near the poles to more than 29 degrees Celsius in the tropics. The maximum surface temperature of oceanic waters depend on many factors like latitude and season. It is heated from the surface downward by sunlight, but at depth most of the ocean is very cold. 75% of the water in the ocean falls within the temperature range of -1 to +6 degrees centigrade and the salinity range of 34 to 35. Under the enormous pressures of the deep ocean, seawater can reach very high temperatures without boiling. The average temperature of all oceanic waters is about 3.5 degrees Celsius. The variations in total salinity and in temperature cause variations in the density of seawater also. Several biotic and abiotic factors can cause the salinity to deviate from the common value of 35. The inflow of river water and rainwater decreases the salinity. Excess evaporation or formation of pack ice causes the salinity to increase. Let us see the salinity and density of oceans. Ionic concentration is the amount of salt present in water and can be expressed in part per million. The classification of water based on the total salt content is as follows. Fresh water may be containing less than 1000 ppm. Slightly saline water may be containing TDS from 1000 to 3000 ppm. Moderately saline water may contain 3000 to 10,000 ppm, and highly saline water may contain the total dissolved salts from 10,000 ppm to 35,000 ppm. Ocean water has a salinity that is approximately equal to 35,000 ppm. Salinity is the saltiness or dissolved salt content of the body of water. It is a general term used to describe the levels of different salts such as sodium chloride, magnesium and calcium sulfates and bicarbonates. Salinity in the ocean refers to the water's saltiness. In oceanography, it has been traditional to express salinity not as a percentage, but as parts per thousand. It is approximately equal to grams of salt per kilogram of solution. In the other disciplines, people use the chemical analysis of solutions directly, and thus salinity is frequently reported in milligram per liter or parts per million. All over the globe, from the top of the ocean all the way to the bottom of the ocean, salinity is between 33 to 37 ppt, or the average salinity of the ocean may be 35 ppt. In 1978, oceanographers redefined salinity with a new property known as practical salinity scale. It is the conductivity ratio of a seawater to a standard KCl solution, potassium chloride solution. Some scientists estimate that the oceans contain as much as 50 quadrillion tons of dissolved solids. If the salt in the ocean could be removed and spread evenly over the land surface, it forms a layer more than 166 meters thick, about the height of a 40-storied building. Salinity affects the marine organisms because the process of osmosis transports water towards a higher concentration through cell walls. Marine plants and many lower organisms have no mechanism to control osmosis, which makes them very sensitive to the salinity of the oceanic waters in which they are living. The main nutrients for plant growth are nitrogen, phosphorus, potassium, magnesium and calcium. Iron is an essential component of enzymes, and it is copiously available in soils, but not in the seawater. This makes iron an essential nutrient for plankton growth. Plankton organisms that make shells of silicon compounds furthermore need dissolved silicon salts, which at 3 ppm can rather be limiting. The ocean salinity at the surface is high, and then salinity decreases until a depth of about 1000 meters. Salinity then increases again slightly with increasing depth. The halocline is a layer of water where the salinity changes rapidly with depth. Salinity is an ecological factor of considerable importance, influencing the types of organisms that live in a body of water. Salinity influences the kinds of plants that will grow either in a water body or on land fed by a water. Organisms that can live in very salty conditions are classified as extremophiles, halophiles specifically. An organism that can withstand a wide range of salinities is called as euryhaline. The degree of salinity in oceans is a driving force for the world's ocean circulation. This world map shows how the salinity of the oceans changes slightly from around 32 ppt to 40 ppt. Low salinity is found in the cold seas, particularly during the summer season when ice melts. High salinity is found in the ocean deserts in a band coinciding with the continental deserts. Lowest salinity is found in the upper reaches of the Baltic Sea. The Dead Sea is highly saline, containing mainly magnesium chloride. Shallow coastal areas are also saline, and also the estuarine environment are also saline. The density of a water sample is a measure of the total mass in a given unit volume. The density of fresh water is 1 gram per milliliter or kilogram per liter, but added salts can increase the density. The saltier the water, the higher is the density. When water warms up, it expands and becomes less dense. The colder the water, the denser it becomes. So, it is possible that warm salty water remains on the top of cold less salty water. The density of 35 ppt saline water at 15 degrees Celsius is about 1.0255, which is almost equal to 25.5. Another word of density is the specific gravity. Density differences among different water masses allow physical oceanographers to calculate the movements of water in the oceans. At depth, pressure from the overlying ocean water becomes very high, but water is only slightly compressible, so that there is only a minor pressure effect on the density of water. At a depth of 4000 meters, water decreases in its volume by 1.8%. Although the high pressure at depth has only a slight effect on the water, it has a much greater effect on easily compressible materials. The relationship between temperature, salinity and density is shown by the blue isopycnal color curve in this diagram. In red, green and blue, the waters of the major oceans of the planet is shown for depths below 200 meters. The Pacific Ocean has the most highest water with densities below 26, whereas the Atlantic has most of the densest water between 27.5 and 28. The density of pure water is 1000 kilogram per meter cube of water. Ocean water is more dense because of the salt content present in it. The density of ocean water at the sea surface is about 1027 kilogram per meter cube of water. Less dense water floats on top of more dense water. Given two layers of water with the same salinity, the warmer water will float on the top of the cold water. Density in the ocean is determined by the temperature, salinity and pressure. Accurate calculations of density require accurate definitions of temperature and salinity and an accurate equation of state. Salinity is difficult to determine and define and to measure. To avoid the difficulty, oceanographers use conductivity instead of salinity. They measure conductivity and calculate the density from temperature, conductivity and pressure. A mixed layer of constant temperature and salinity is usually found in the top 1 to 100 meter of the oceans. The depth is determined by wind speed and the flux of heat through the sea surface. Understanding of the properties of sea water is very much needed to determine many of these parameters in oceanographic studies.